looking at physics form 2, the two topic turning effect of a force and equilibrium and center of gravity. So if you are joining me for the very first time, I take this opportunity to welcome you and thank you for joining me. So under turning effect of a force, we'll start with the moment of a force, and we'll start by knowing what is moment. So we'll define moment of a force, and we normally say moment of a force is the turning effect of the force. So the two words are used concurrently. So when we talk about moment of a force, we are talking about the turning effect of a force, and it is defined as the product of force and the perpendicular distance from the point of support. Moment of a force. So the product of force and the perpendicular distance from the point of support. The product of force and the perpendicular distance from the point of support. Taking a case, for example, the diagram I have here. So if we have a force F here, and this is the pivot, so this is the distance. So the force is being applied at this point, and the perpendicular distance is from point where we have the pivot to where we have the force. And therefore we'll talk about the moment of a force taken from this point of support. And as we are talking of, as I'm saying, it should be perpendicular from this point of support. So mathematically, therefore, we'll say moment is given by force times distance. So the force should be in Newton and the distance should be in meters. So then from there, we'll talk about the next thing, and the next part is now how we take moment. So we have so many cases of examples where we talk about moment, and before we talk about those cases, we'll talk about the SI unit of moment of a force, and the SI unit is a Newton per meter or Newton meter, since we are talking about the product of force which is in Newton and the distance which is in meter. So we talk about the SI unit as the Newton meter. So the other thing is about the factors that affect moment of a force. The factors are factors affecting moment of a force. So we'll talk about two factors. So one is the amount of force. So the amount of force, so the more the force, the greater the moment. The lesser the force, we'll also have the moment being less. And then the other point, the other factor, we have perpendicular distance. Perpendicular distance. So perpendicular distance, for this reason, we have the force or the moment would increase with perpendicular distance increasing. So in short, moment is directly proportional to the force and also to the perpendicular distance from the point of support. So case examples where we have our forces producing turning effect. So when you are opening or closing a door, so you apply a force against a certain distance. That is an example of moment. Again, when operating or when we talk about a pair of scissors, or again when children are playing in a seesaw, that is a moment of a force in practice, and so many others. So from there we'll talk about the principle of moment. So principle of moment and a principle of moment. I'll talk about now how we take moment. We have agreed that moment is taken from the pivot to where the force is acting. So when we talk about the principle of moment, so if we consider a bar pivoted at a certain point, we call that equilibrium, and then we have some forces or some masses hanged on both ends, two for that case. So two forces, and those forces, their mass are known, so we'll call them weight 1, weight 2, then these others weight 3 and weight 4. And then we have these, or we give these for the weight 1, we give it distance from the pivot, we call it d1, and weight 2 we call it its distance d2, and then weight 3, its distance from the pivot, we call it d3, and the other weight 4, we call its distance from the pivot d4. And now how are we going, or how can we take moment from in such a case? So we'll be talking about, or I'm talking about force from the pivot, or force times distance from the pivot. So if I'll say, or if I say we have this force W3 and W4 taking this bar in a clockwise manner, so we call those clockwise, and we'll talk about, or they are taking the bar in a clockwise way, while W1 or weight 1 and weight 2, if they are allowed to hang on this bar, it will be anti-clockwise. It will be anti-clockwise. By that I mean, so when we are taking this moment from the pivot, and if this bar is at equilibrium, it means they are balancing. And that is when we we bring this into conclusion and say the sum of the clockwise moments and the anti-clockwise moments are equal. And by this I mean, if you are to take individual moment, we'll take the moment for W3 and W4, and we'll say W3 times distance 3 plus W4 times distance 4. By W we mean the weight 4. This should be equal to W1 times distance 1 plus W2 times distance 2. So in short, what I mean, or in short what we get is that the sum of clockwise moments is equals to the sum of anti-clockwise moment. So the sum of clockwise moment is equals to the sum of anti-clockwise moment, So, and this is what we call the moment, or the moment of a force. And for that bar to balance at that particular point, the sum of clockwise movement should be equal to the sum of anti-clockwise movement, and that gives us the summary about the principle of moment. And the principle of moment states that for a system in equilibrium, the sum of clockwise movements about a point is equal to the sum of anti-clockwise movement about the same point. And which point are we talking about? We are talking about the same pivot. So we are not changing the pivot, but we are talking about it as one. So therefore that takes us to the conclusion about the sum of clockwise movement, or about the principle of moment, which states for a system in equilibrium, the sum of clockwise movement is equal to the sum of anti-clockwise movement about the same point. And that takes us to an example. So we look at an example on how we apply moments, and then that will take us to the next step. So if we have a question, or if we have a bar which is balanced at a certain point, and some forces are acting on both ends, so we are supposed to consider, so force 1, force 2, force 3, and force 4. So we are supposed to consider the force that is acting, that is clockwise, and the force that is anti-clockwise. So the sum of clockwise movement should be equal to the sum of anti-clockwise movement about the same point. So without changing the point, which is now our pivot. So having or doing an example will take us to the next example, or the next part. That is, we are talking about the topic equilibrium and center of gravity. So in short, the principle of moment, or the principle of moment, states that for a system in equilibrium, the sum of clockwise moment about the same point is equal to the sum of anti-clockwise moment. So an example, so we have I have a question here, a girl. So a boy of mass 40 kilogram sits at a point 2 meters from the pivot of a seesaw. Find the weight of a girl who can balance the seesaw by sitting a distance of 3.2 meters from the pivot, taking gravitational field strength to be 10. So as I'm saying, we'll talk about, so the formula, we are saying sum of clockwise movement is equals to sum of anti-clockwise movements. So in this case now we are going to look, is it the girl or the boy who is moving the pivot in a clockwise manner? And if you may look, so when the girl is sitting at this position, she is the one who will push the seesaw in a clockwise manner, and therefore we are going to take the force of the girl, and in this case we are not aware, so we call it F. We multiply that by 30 meters, the distance of the girl from the pivot, and this will be equal to the force of the boy. So we change the weight of the boy into a force, so 40 by 10 to make it a force, and then we multiply by the distance from the pivot, which is 20 meters, and then so this is 10, so this is 400 by 20, and then this is 30 F. So the force is 400 times 20, we divide by 30. So we are saying that the weight of the girl will give us the clockwise moment, and that of the boy will give us the anti-clockwise moment. So for them to balance on the seesaw, then the moment should be equal. So finding the F from your calculator, so we get 400 by 20, then we divide these, we have the answer, divide this by 30. So we get that the force of the girl is 266.6 or 0.7 Newton. But remember, this is not a weight. Oh, this is weight. So the girl's mass, so mass of the girl, so we are going to divide this by 10. We divide by 10 and we find that the girl's weight or mass is 26.67 kilogram. 26.67 kilogram. So that marks the end of that brief about the topic. So maybe we can talk about some other things in the same topic. So under the same topic, we talk about the parallel and anti-parallel forces, and majorly we talk about the anti-parallel forces. So when we talk about anti-parallel forces, or we call it a couple, this refers to anti-parallel forces. So these refer, so we call it a couple or couples. So anti-parallel forces refers to equal, parallel but opposite forces. So equal, parallel but opposite forces. So when you talk about equal and parallel opposite forces, it means the total moment of anti-parallel forces is the product of one of the forces and the perpendicular distance between the forces. So if we have such a case, and we have a force F and another one here, so this is the distance between the two forces, the two anti-parallel forces, the distance. So for moments of such a case, or moments of anti-parallel forces, will be the one of the forces, one of the force times the distance, the separating distance between the two forces. And when we talk about one of the forces, we mean one of the forces because these forces are equal but opposite and parallel at the same point. So which are these situations when we talk about, or the examples of a couple or anti-parallel forces? We have so many cases, example like the force applied when opening a water tap. So that force that is involved is a couple because you apply two forces in different direction, or the forces that are opposite for the tap to be opened. Another case is a force applied on the steering wheel of a car. So you apply one of the force using your left hand side there, and the other one you pull, pull. So we are talking about that's the steering wheel. So you apply a force on this direction and another one on this direction for the wheel to turn, and then so the distance, the separating distance for that case is the diameter. So if this is force and this is force, so the moment will be one of the force times the distance, which is the diameter of that wheel. So again, force applied on a bicycle handle. So when one is riding a bicycle, so we've talked about steering wheel. A bicycle handle. Again, in a bicycle handle, we have one of the force applied to that direction, while another one applied to this direction, and of course we have the turning point here. But again, we'll take the distance, the whole distance d, and we call it d. So that marks the end of topic that is the turning effect of a force. So they are so much related with the other one we are about to discuss. We talk about equilibrium and center of gravity. Equilibrium and center of gravity. So under equilibrium and center of gravity, we talk about similar things to turning effect of a force. So we talk about the center of gravity. So as we have equilibrium and center of gravity, so we talk about the center of gravity and we abbreviate it as COG. So we talk about COG, and the center of gravity of a body is actually where the whole weight of a body appears to act, or the position, the point where the whole weight of a body appear to act from. So if you balance a meter rule, for example, using a string or a thread, you'll realize that it will tend to balance at the 50 centimeter mark, because we know that the meter rule is uniformly made. So it will appear to balance at the 50 centimeter mark, and that means at that 50 centimeter mark, that is where we have the center of gravity of the meter rule. The center of gravity of that meter rule. And actually we can use our hand and try to balance the meter rule, and the meter rule will not fall off on either side. So if we have again a rectangular piece of wood, and you join its diagonals using a ruler, where the diagonal meets, you try to balance that using one of your finger or a pen. You'll find that the piece of wood would balance, and therefore it means that is the center of gravity, or the COG, of that rectangular piece. If you have a square piece, again we join its diameters, not diameter but its diagonals, they meet at a point, and again that is where we have the COG, and that's where the weight of that particular object appear to act. If it is a circle, we join two diameters, again that's where we have, and I'm sure we've looked at these in class under some different shapes, and where the position of their center of gravity appear to act. We also know that weight is given by mg. So the weight of an object acts at that particular point. That is the point where all or its weight act from. So then we move on now, combining the COG and what we learned earlier about turning effect of a force. Therefore, it means any piece of wood or a meter rule has weight. And that takes us to a question we'll be able to look at and solve that involve now weight of the rule, of the meter rule. So in this question here, the figure 1 shows a uniform meter rule pivoted at the 30 centimeter mark. It is balanced by a weight on 2 Newton suspended at the 5 centimeter mark. So one thing we've been told, it is a meter rule, so its length is 100 centimeters, and therefore we've said the weight 100 centimeters all 1 meter. So we know at the 50 centimeter mark, that is where the weight of the meter rule acts, and therefore in this case, under equilibrium and center of gravity, we will consider the weight of the rule at that particular mark. And therefore, when we talk about the sum of clockwise movement should be equal to the sum of anti-clockwise movement, the weight of the rule is also included. And in this case, so for us to solve the weight of this rule, because the question is calculate the weight of the meter rule. So we are going again to consider sum of clockwise movement, and we say sum of clockwise moment is equals to sum of anti-clockwise moments, and that is the point we talk of. Now I will talk about clockwise moment. So the weight, if pulled, is the one which will give the clockwise moment. So we'll talk about the force, which is W times the distance from the pivot. So the distance from the pivot is this distance, and we know this is the 50 centimeter mark, and therefore 50 minus 30, we have 20, so 20 over 100 to make it meters. This should be equal to, we were told it is balancing at this 2 Newton is at 5, so the remaining distance is 30 minus 5, so this is 25, and therefore we are going to talk about the force 2 Newton, we multiply by the distance 25 divided by 100, and now taking these to the calculator, we have this as 0.2 weight W is equals to we have 2 by 25 over 100, we have a half, which is 0.5, so 0.5. So to get W, we divide by 0.2 and by 0.2, so we get weight to be 0.5 divided by 0.2, and we get the weight of the rule to be 2.5 Newton, 2.5 Newton, and that will start to be the answer. So another example, we have one here, and we have the system in the figure 2 is in equilibrium. In equilibrium means it is balanced at the center. Determine the weight of the bar. So the weight of the bar tumesema the weight acts at the center, so at the 50 centimeter mark. So again we'll say sum of clockwise moment is equals to sum of anticlockwise. Is equals to sum of the anticlockwise moment, and clockwise moment weight is providing that, because at this point the bar would move in a clockwise manner. So then times the perpendicular distance. So if we have this being 30, then at this point we have 50. So it means this is 20 to make it to 50. So we are talking of 20 over 100. This should be equal to the sum of anticlockwise moment. So this one gives the anticlockwise moment, so 5 Newton, and it is at the edge. So 5 times the distance from the pivot, which is 30, so 30 all over 100, and then we solve for W, and we find that this will be 0.2 W is equals to 0.3 times 5, 1.5, and dividing by 0.2 and by 0.2, we get that W is equals to 1.5 divided by 0.2. W is equals to 7.5 Newton, and that is now the weight of the load. Finally, another question on another dimension, and we'll talk about another one, or this one. Figure 3 shows a uniform bar of length 1.0 meter pivoted near one end. The bar is kept in equilibrium by a spring at balance as shown. Given that the reading of the spring balance is 0.6, determine the weight of the bar. Again, we are talking about sum of clockwise moment. So sum of clockwise moment being equal to sum of anti-clockwise moment. That is our point to take, and we are also talking about, or that should be the formula we consider. Sum of clockwise moment is equals to sum of anti-clockwise moment. So then we need to identify which are clockwise moments and which are anti-clockwise moments in this case. So the spring balance offers, or is holding the bar from falling off, so it is offering the anti-clockwise moment, because if this is the center, the weight is acting at this point, so the weight is moving in an anti-clockwise manner. The weight of the bar, this is anti-clockwise, while this is preventing the beam from falling, so it is acting in clockwise manner. So the clockwise manner is now where we have the spring balance, and we have, so the force times the distance, and the distance we take is from the pivot, so from this point to the pivot. Sorry, we forgot to indicate this was supposed to be 10 centimeters, not drawn to scale. So we have and we are talking of a meter rule, so that is 100 minus 30, so making this to be 70. So therefore we are going to talk about the force, and the force is actually what is the reading in the spring balance. So 0.6 we multiply by the distance, which is 70 over 100, and this is equals to the sum or the anti-clockwise movement, which for this case is the weight. So the weight, of course, this is at the 50 centimeter mark. So we're going to talk about the force, which is weight. We don't know, or we are trying to find the weight. We multiply by the perpendicular distance from the pivot. So this distance is actually, so if the whole of this is 50, so it means 50 minus this 20, we have 30, which is up to this point. So we have times 30 over 100, 30 over 100, or to change that into meters. And computing these, we get 0.6 multiplied by 70 over 100, and we get this to be 0.42. This is equals to 3 or 0.3 W, 0.3 W. So we divide by 0.3 and 0.3, and we get that W is equals to, so 0.42 divided by 0.3, and we get the weight to be 10 Newton, and that now will be the weight of the bar, the weight of the bar. So that marks the end of the calculation. Maybe to briefly talk about the other things we talk about in the same topic. In about 5 minutes we end. We talk about the equilibrium states. The equilibrium states. And under equilibrium states, we talk about the states of equilibrium. And we have 3 states of equilibrium, which is the stable, unstable, and neutral. So equilibrium states. So under equilibrium states, we talk about the types of equilibrium states, and before we talk about that, so the state of equilibrium refers to the state of balance of a body. The state of balance of a body. And we have 3 states of equilibrium, namely stable equilibrium. So one, stable equilibrium, and a body is regarded to be stable if on application of a little force it tends to get back to its original state, because it wants to remain stable. So if you try disturbing it, it will tend to get back to its original states of equilibrium. So that is about stable equilibrium. So when you talk about unstable or unstable state, a body is in unstable equilibrium if it's on being disturbed, it does not return to its original position but occupy a new position. For example, when a funnel is at that state and you try to push it a little bit, remember its center of gravity is up here, so it will fall off and it will not get back to the state it was initially, because it is trying as much as it can to lower its center of gravity, and on falling off it lowers the center or its center of gravity. So 3, we have neutral state, and under neutral states of equilibrium we have, for example, a ball. So a body is said to be in neutral equilibrium state. If on being displaced a little bit, it occupies a new position similar to the original state. But note, on this case, the center of gravity does not change. So if a ball is kicked along the ground, it will roll, occupies another state or occupies another point, but its center of gravity will remain to be where it was. And then we say for that instance, that ball is at stable equilibrium. So there are some conditions for equilibrium. We talk about condition of equilibrium. So the sum of forces on the body in one direction is equal to the sum of forces acting on the body in the opposite direction. That is one condition of equilibrium. Another condition of equilibrium, we have the sum of clockwise movement about a point should be equal to the sum of anti-clockwise movement about the same point. Those are the two conditions of equilibrium. And then lastly, we will talk about factors affecting stability of a body. Factors affecting stability of a body. Factors affecting stability of a body. And these factors are: one, position of center of gravity of a body. So the lower the position of center of gravity, the more stable a body is. So if the center of gravity of a body is too low, that body is said to be very stable. And then we have the base area. The base area. A body is more stable when the base is wide. A narrow base makes the body to be less stable. A narrow base makes the body to be less stable. And we have different examples of application of stability. And one, we all talk about racing cars, e.g. the Formula 1 cars. They are made to be so short and with wide base. One reason they are short to lower their center of gravity, so enhancing stability. They also have a wide base to make sure the center of their center of gravity is lowered. When you talk about when making a stool is made in such a way that its legs appear to separate from the, or we talk about it's made in that state. So we are widening we are making the legs in that kind of a manner to make sure that we increase the base area and hence enhancing stability of that body. Enhancing the stability of that body. So we also talk about many other things. For example, when you are jumping off from a stool, so you are at this position, you want to jump down here. There are things you do. When you want to jump, you just first make sure that you lean a little bit. After leaning, by leaning, you are trying to lower your center of gravity. Again, on landing, you make sure that your legs are wider apart. Why? So you are separating your legs to increase the base area, and hence making sure that you lower your center of gravity. You lower your center of gravity. So in that regard, or in that case, you are making sure that you get short, so lowering your center of gravity, and then you make sure that you lower the position of the center of gravity. So I will mark the end of our lesson at that point. So I was online. I was live on YouTube and on Facebook. So if you like my work, kindly subscribe to my YouTube channel and like and share to your friends. Have a good afternoon.